Welcome to this short video on Odeon 13 Combined. I'm Claus Lyngen Christensen, and in this short video I'll introduce you to some of the main features of Odeon Combined. So we are inside the main window of Odeon, and first of all we should get a geometry into Odeon. There are different ways of doing that. We can use the SketchUp plugin that comes with Odeon, or we can import geometry files from CAD programs in one of these formats, DXF, which is a very common one, or indeed we can also use the native scripting format of Odeon. In this video I will try to import geometry in the DXF format, and the DXF format is the drawing exchange format, which is a very common exchange format for CAD software like AutoCAD, Rhino, Revit, and so on, many more. So let's try. So I have an example file here, which also comes with the demo version of Odeon, so you can try it for yourself. We try to import it. And here is the import dialog, where you can select which unit you would use. And we know that it's meters in this DXF file. You can also change the orientation of the geometry, for example, if it doesn't fit to your purpose. Invert the axis and so on, and a lot of other stuff. So let's import the geometry, and here we have the geometry. We can view it with layers because the layers are preserved when importing the geometry. And then we should assign, first of all, some sources, some receivers. We should define materials as well. So let's go on. I go into the source receiver list, and here I can define point sources and also other types of sources, and as well as receivers. So I opened the point source editor, and I can select my source position either by typing the specific coordinates or by using this grid up here to assist me in putting my source at a meaningful location. I can also use the Align Expert. In this case I want to put my source 1.6 meters above the floor. So there you see, we have our source 1.6 meters above the floor. So we defined a source and its position. We should also have some receivers. Let's put a receiver first, part of the audience area here. Again, I want to use the Align Expert to put my source, in this case 0.6 meters above this audience box you can see here. So there we have our first receiver inside the room. So that was one receiver position, and we would want to have some more receivers in this room. So what we can do is we can make use of this tabulate selected source or receiver, and because I selected the receiver list, it would suggest that you want to tabulate the receiver. You can see here is a suggested position of a new receiver. And let's try to define some more receivers like this, or using the scroll wheel. I want to have receivers with 2 meters between them. You can see that they are sticking outside the geometry, but what we can do is we can let them fall from a higher height. So if we drop them onto the audience area, then they will be at the same height as the original receiver. So we have a line of receivers here. We can also rotate them, give them a little bit of azimuth angle, like this. And you can see that still they are at the right position. So that's not too bad. So let's save these receivers, and we now defined sources and some receiver positions, and we are ready to go. Having done this, we should define some materials. As a starting point, I want to define just 10% absorption to all surfaces. So we select this, and then we can change a few of our materials in the geometry. So we can use the layers for that. So the layers that came with the drawing from, in this case, AutoCAD, I think. And we could say that we want some audience area on the audience surfaces. So I go to the material library here and search for audience. here we have some different types of audience area. So I take audience area, lightly upholstered seats, and assign it to all the visible surfaces. And then we can go on and assign materials to other surfaces in the room, and I want to give these side wall reflectors another material. So here is the side wall reflectors, and we could assign plywood, for example. And again, I assign it to all the visible surfaces in the geometry. There you go. So we defined our materials, 3 different types: 10%, plywood, audience area. And I will not go more into details now. First calculation we can do now that we have assigned materials and we have defined the source is the quick estimate. And it gives you a rough idea of what will be the reparation times in this room according to the Sabine and Öring and Arapakadis formulas. So very simple calculations, but giving you a first indication of what is the reparation time. We also have other graphs, like you can see which types of materials and how much is installed in the room, or where could we put more absorption in the room, or what type of absorption coefficients materials has been defined in the room. So that was the first calculation in the room, and we've assigned materials, defined sources and receivers, and I say these. Now we could enable all of our layers so we can see the full geometry again. What we can do when this is done is first we could make some visualizations. A useful one is this 3D Investigate Rays, and you might consider it kind of a gimmick, but it's also quite a useful tool because it allows you to verify that your geometry is watertight, so that rays are not escaping through holes in the geometry, and it seems fair that this is a fairly watertight geometry. And what you can also use it for is to verify that you haven't put your source below the floor or inside a column or a box or whatever, so that you have a valid source position, so it can easily be seen that this works. Another visualization tool we have is the 3D billiard, and it plays with a number of billiard balls and shows you how they reflect in the walls of the room and how sounds get scattered by surfaces depending on the size of the surfaces and the material types and so on. Quite a neat visualization, and you can also look in different directions in the room, so having a vertical radiation of these billiard balls or into the 3D space as well. So this is the 3D billiard display, quite easy to use. Another thing we can visualize is reflector coverage, and I will shortly show you how to do that. Let's search for the reflectors in the room. So we have side reflectors, which is not the ones that I want to show now. We also have sidewall reflectors, and we can multi-select these in this list. And then we can see that these were the reflectors we selected. And finally we can do a visualization of reflector coverage. You can either just visualize where the reflection will occur, so where the reflection will be reflected to the surfaces. You can use a different number of rays, and you can also show the rays themselves. In this case you'd probably use fewer rays, like this. And you can define which reflection order you want to use, or that you want to visualize your reflectors with the color by layers. If you have many different types of layers and so on, you might prefer this in order not to get too many different colors. So these are the visualization tools that we have there. But we're ready to go now. We should go into the job list, which is where the real calculations in ODIN takes place. And here we have, in the combined edition of ODIN, we have single point, multi-point, and grid response. Let's try and calculate a single point response, which is the most detailed calculation we have inside ODIN. So it will give you point response calculation with a lot of different results. Let's have a look at the result display. And this is not by accident. I wanted to show you, because it's a common error, that here we get stars for the results, and that's because the impulse response is too short in order to calculate T30, which requires at least 35 decibel of the decay to be present. So we go into the room setup, and we should specify a more relevant impulse response length, and we could select 2 seconds, as we learned before that the reverberation time is something between 1.6 and 1.8 seconds. This should be sufficient. So let's save it and do the calculation again. So here we have a fairly fast calculation result, and you can see all the results are present for all octaves. We have decay curves. We only used 1000 rays, so it's not as good as it could be if we used somewhat more rays, but it's a fair result, a fair quality. We have this display that shows from which directions energy comes in different time intervals. We have reflection density, which helps you to see if you have sufficient calculations in your calculation. So we suggest that you have at least 25 reflections per millisecond, but if you want to have a good quality result, then 100 reflections per millisecond is probably better. The 3D reflectogram is where you can trace down how early reflections are generated. So if we click a reflection here, then press F8, you'll see that, okay, this was a reflection which came into the left side wall, into the right side wall, and then hit the receiver. Here we have the image source. Then we have some detailed curves which helps you investigate diffusivity and echoes and so on. Last tab I want to show is the BRIA. It's the binaural room impulse response. And the binaural room impulse response is what you get if you go into a room, clap your hands, and then record it at some other receiver location. What happens at the left ear and the right ear of a receiver at a dummy head or a living person with microphones in each of the ears. And then you might get something like this: left ear, right ear. And by using this as a filter to a process we call auralization, you can listen to how will sound at this receiver position when the source is playing some signal. And listening through this through headphones, then you'll get a kind of 3D experience which is very realistic. Let's try to do that. So we can press this streaming convolution button and listen to some signal.
The Athenian agora and the South Slope. It was during the 5th century before Christ that the Athenian agora began to take shape as a commercial and civic center of Athens.
And we can also listen to
About the middle of that century, the center
so
of public theater activities was moved from its temporary the Athenian agora and the South Slope. It was during the 5th century before Christ that the Athenian agora
or indeed to some other signal, or listen to it in another receiver position if we have calculated such one. So it's a nice way to present how the acoustic sounds to laymen that might not be acousticians, so they get an understanding which goes beyond just reverberation time. Other results we have here is the multipoint, and then we need to check this option and calculate it. And it's simply the same results, but for a number of receivers, and then not so detailed as before. If we open this multi-point response calculation, then you can see that we can see which point they were calculated for. We can group receivers, so we can get statistics for a selected group of receivers. We can view parameters here, so there's a number of different parameters available calculated at the same time for these different receivers. We have parameter versus distance in a graph, statistics for selected parameter, spatial decay curves, so how much is the damping per distance doubling, STI versus distance, speech transmission index, and then parameters listed as numbers, And we can also import measured data, so we can compare measured and simulated parameters. And indeed, Odeon has a complete measurement facility built into it. So Odeon is a combined simulation and measurement software for room acoustics. So that was very shortly multi-point response. We also have grid response, which can give you a mapping of the audience area or a selected area. And let's try to build such a grid. We can take this auto option inside the defined grid. And then Odeon will suggest some surfaces which can be used for this grid. I will just exclude some of the surfaces that Odeon suggested. Ceiling should not be included. And let's go on to this button here and see there's a few reflector surfaces I don't want to include either. And let's see if we are satisfied. This seems like a very meaningful grid to me. I just want to change the distance between receivers, so we get a grid like this. So each of these squares is a receiver point where Odeon will calculate parameters. If we go back into this job list and check the grid option, then we can indeed calculate this grid, and it takes like 1 minute because there's 1067 receiver points we need to calculate. It's not so bad. While we're waiting, I can show you the OpenGL display for different receivers. So here we have our receiver points we defined before, and we can look into the space, and you see different colors of the surfaces, and those colors are actually derived directly from the acoustic properties we assigned. So we map the reflectance of the surface into red, green and blue depending on the frequency range, low frequency, mid frequency, high frequency, and that gives you the color here. So red surfaces are reflecting very well low frequencies, blue surfaces are reflecting very well high frequencies, and grayscale is neutral with respect to frequency. Black means absorbing everything, white means reflecting everything. So you get a very good overview over the different types of materials you have installed in the room, and it's also a nice way to spot if there's an error in your assignation. For example, if a surface down here had a completely unexpected color, you probably did something wrong. So that is this OpenGL display, and while we were looking at that, we finished the calculation, and we can view this grid, receiver grid, and the different parameters, sound pressure level for example, at different frequencies, and a lot of different other parameters are present, like clarity or STI or reverberation time, early decay time, and so on and so on. This grid might be good for spotting weak areas in the room, and it's also very nice for visual presentations, but when you're designing an auditorium, you might want to use some statistics saying that, for example, 80% of the receivers should be within a certain limit with respect to SBL and reverberation time and so on. So here we have the cumulative distribution function or fractal graphs, which will help you set up some design criterions. So this was very shortly the main calculations in Odeon. Odeon is also a measurement tool, so we do have a sweep tool that helps you measure impulse responses using the sine sweep method. And we have the result display here where we can load an impulse response which has been measured. And we could take this gym hall and look at a measured impulse response. So this is the impulse response at 1000 Hz, and we can also select the octave band, broadband there, and 8 kHz and so on. We have the raw decay curve, which is essentially the squared impulse response, and what we see here is that Odeon detects the onset time. It also detects the truncation time, where the impulse response falls into the noise floor. We have decay curves where you see the Schrödinger curve, the integrated Schrödinger curve, from which we derive reverberation times, and a decay curve for each octave band, where you will see that the decay is truncated at different levels due to the background noise. That happens automatically. But apart from that, things looks very much the same like in simulations, so it's easy to compare simulations and measurements. We have numbers like you saw before in the single point response, and we can have it as bars, and we have a frequency response here. So that was very, very shortly the measurement tool in Odeon. One thing I want to mention is that it's very easy to add these measured data to a multi-point job like you saw before, so you can easily compare measured and simulated results. So all the parameters you see in here is added automatically to your multi-point response you saw before, making it very, very easy to compare simulations and measurements. So I think that's largely what I want to say about Odeon Combined version 13. A little thing we have in another video here is the new feature, Genetic Materials Optimizer, which helps you trim a model so you get the same simulated results largely as you measured in the room by optimizing the materials to match reality out there. So that's the main features of Odeon, I think. We have a number of other videos available on our homepage, which might give some more details on selected features in Odeon. But for now, I want to say thank you for taking the time to watch this introduction video to Odeon 13 Combined.